This is a continuation of the AASHTO passive pressure calculation that we've been working on, where we took the charts that are in AASHTO and we digitized them, and now we put them in Excel. Let's start making some use of some of this data that we've been acquiring. So I'm also starting to build an actual calc package that includes text and pictures and things like that. So in AASHTO, the two figures computational procedures for passive earth pressures for vertical and sloping walls with a horizontal backfill, and for passive pressures for a vertical wall with a sloping backfill. So I I'm starting to set it up so that if somebody were viewing this as a live sheet, they could double click inside the Excel portion of it, and it would pull up the data just like that. All right, let me close that out. Or if you're looking at this in a PDF file, then we could put the Excel spreadsheet, which I actually have made a copy of it here, so you could put that in an appendix so that a reviewer or a third party could actually see the underlying data that you used to create this thing. So what AASHTO also says is that if you don't have these conditions, either horizontal backfill with a vertical or sloping wall, or a sloping backfill with a vertical wall, then you can't use these charts and you got to use something else. And so I've kind of programmed that into the calculation package so that it actually takes that into account. So it says you have to use the wedge theory, which is basically using either the Rankine or the Coulomb passive coefficients, and use a factor of safety of 2. So that's generally how you do it. Okay, so we got all the data into this Excel component, and now I am pulling the data out of Excel and putting it into a format that MathCAD can understand. So the very first, let me actually change this a little bit. So if you go over here and save this and then close it, yeah, MathCAD, um, the picture that comes back in the MathCAD is where you left it off. So you can see that for this particular video, I'm just concentrating on figure 1. I haven't programmed anything in figure 2. So I just want to concentrate on figure 1, which is talking about those theta values. And theta is the angle of the wall. So there's a couple things we've got to do. Number one, if you have an exact theta angle, and they're in 10-degree increments, and you just happen to have one, then you ought to be able to calculate the passive pressure. But that's typically not what happens. What typically happens is you're going to have some intermediate value. So you're going to have to be able to interpolate. And there was a couple ways I looked at doing this. One was I thought, well, I could just make polynomial functions or a Los function out of this thing, so that once I calculated what theta is, and then I could have the function take me to the value that I'm looking for, and then if I needed to, I can interpolate. And then once I actually went down that road a little bit, and first thing I knew, I had blown up MathCAD, and because the computations were getting so big and extensive that it was kind of bogging down and basically just kind of shut down on me. So I needed to piecemeal this thing a little bit better and not use so much computational power. And so I decided to do it with just lookup tables. So not only do you have lookup table capability in Excel, but MathCAD also has lookup table capability. In MathCAD, a table is the same thing as a matrix or a vector. Um, so let's talk about that in a little bit. But let me get all these variables. So what I did was I created a set of variables where I took each of these columns in the Excel template and I gave it a variable name. And so I want to point out something that's pretty important here. So if I click on this area, you can see there's a little half-closed square. Well, not half-closed. It's not completely closed. There's a three-sided square there. And what that's indicating is that that is an index value. And an index value is tied to a vector or a matrix. And that's different than a variable with a subscript. So let me show you what a variable with a subscript. Let's say Vx, and if I hit Control underscore and type in 1, first it doesn't recognize it, but let me let me say, okay, let's equal to 2. Let me just, so I can actually see it. Well, it doesn't even want to do that. Okay, so what it's saying is I'm in the output portion of the Excel component, so I can't um, do anything like this. Let's see if I'd have to type in that. So let's don't worry about that right now. So if you just look at it, you see there's no little unclosed square like there is over here. And the thing about this is, actually, let me go down here where we can do that. So if I type in VX control underscore 1, let's say I'm set that equal to 2. Okay, that is a variable. There, it returns, if I were to type in VX control underscore 1 and hit the equal sign, it returns a scalar value. If I were to define this as a matrix, let's say VX, and then I hit the brace next to the letter P on the keyboard, now you can see that little unclosed square. That's telling me that I'm putting in a vector or a matrix. And if I call this 1, and I said, okay, that's equal to 3, for example, and then I type in VX, and I hit the brace next to the letter P and type in 1, and then the letter equals, okay, well, that is a matrix or a vector. All right, let me make that a little bit clearer and actually input vector value. Let's say that's 3 and 4. Okay, so now you can see very clearly that it is a vector. Okay, and so this 1 is an index, not a variable subscript. And there's a big difference in MathCAD, and so you need to be careful. So what I'm doing here, let me erase this. What I'm doing up in the output section of the Excel component is that I'm creating vectors. I'm not creating variables, I'm creating vectors. One of the last things that I want to mention is that I can create a variable name, let's say VX, control underscore 1, and then if I hit the brace next to the letter P, I can make that an index. So I can have a variable with a subscript that has an index as well. And the difference is that when you click on it, you can see that the little square is not closed. So that's telling you that I haven't, there's a variable, but there's also a matrix or a vector associated with that variable. All right, so that's real important. So all these things these are all index subscripts, and they take each of the columns in the Excel component inside of MathCAD and pulls that out into MathCAD itself. So if I were to go here and type in, let's say phi F control G control underscore table and hit equals, then you can see I've got that now as a vector. All right, so that's how I got all my data out, and I've got 91 data points because it goes from 0 to 45 in half a degree increments. And again, I think I've decided that that's, that should be plenty good for most 99.999% of everything we do. We typically don't determine the angle of internal friction much below a whole degree, or sometimes even 30, 32. It's just kind of tough to get those that kind of precision or accuracy. All right, so let's put some numbers in. So we've got the data. I've got it in Excel. I've pulled it out into MathCAD. Let's start programming an actual calculation. So I need to start entering some numbers. So if I put in the angle of the wall batter as defined by figure 1 here, let's just say it's vertical, so I'm going to call that 90. And the other thing I need to enter is that I need to enter the angle of the slope, and we'll call that beta. And then I need to enter the angle of internal friction of the soil. All right, so I'm entering the angle of internal friction as 30 degrees, but my chart is dimensionless, so it just has a number 30. So I've got to take that degree symbol out, and I do that just by dividing by 1 degree, and you can see here that that turns it back into a scalar value instead of a scalar value with a unit. So it takes the units out. So let me close that. All right, and then although this little calculation is not really important to what I'm doing now, it will become important later because there's going to have to be some reduction factors where you monkey around with that. So I just right now I've just got a value that I just plugged in for grins. All right, so now I've got this little function that I created called chart check. So chart check says, okay, examine the situation that you've input the numbers in and determine whether or not you can actually use the AASHTO figures. So in this little program I wrote, I've got an if statement. Remember, anytime you use there's certain keywords that you have to go up here and program. You can't just type them in, otherwise you'll get an error. So there's my if statement. So if beta is equal to 0, and this little 0 is the control equals, so you can see it's a Boolean 0 and it's bolded. So if beta equals 0, and then this little symbol is and, right there. So here's all your Boolean operators, an element of, equals, the exclusive or, logical not. You know, you've got a lot of different things to choose from here. So if beta equals 0 and theta is between 50 and 120 degrees, then this little function will return the value, use figure 1. If it's not, then it goes and checks the next condition. So if beta is greater than 0 and theta is equal to 90 degrees and beta is between -1 and 1, then we can use figure 2. So for example, if I had theta at 90 degrees, but my beta phi value that I just calculated here was, say, a -1.1, then that's going to be a problem. As a matter of fact, let me check that and make sure that works. So let me type in B, Control B, F, Control G, equals, let's say 1.1. All right. It should say use figure 2. So, oh, I don't have my beta. I didn't set my beta greater than 0. Let's say it's 10. So beta is greater than 0 and B, so B phi is less than 1. I may have to look at that. I'm thinking I should be getting this little thing, use figure 2 instead of the use the wedge method. Well, oh. Let me just let that do it for me. There we go. Okay. So I was confusing myself, but the great thing about MathCAD is that it never gets confused. All right. So now I've got this right, and let's say if let's go back up and change that to 80. And that should tell me, I think, that, yeah. So I got to use the wedge method. All right, so my chart check is good. It will tell me if I've got the right values, and it will tell me which method I've got to use. So if I'm actually working on a real problem and I enter those values of beta and my theta angle, then it should say, hey, you can't use the charts. So we'll have to, so you would stop at that point and move on to another calculation, or eventually we'll have it already set up in this particular MathCAD template. So let me go back and reset this stuff because I want to deal with the horizontal backfill. And let's just leave it right there for now. So I've got this, use figure 1. Okay. So now, so I've created these things, and so all I did here was that I regurgitate what I actually did up here in the MathCAD thing. I said, okay, v sub y1 with an index of 1 is actually row B, which is the curve for the 120 theta. All right, so that's all I'm doing here. It's just reminding myself when I was putting this together what these indexes actually mean. All right, and so then I started putting this program together. So the way the program works is that KP figure 1 is going to go in. I'm creating this function called KP figure 1, and first thing it does, it goes through an if statement and says, okay, if chart check is equal to use figure 1, then it's going to give me all this data. Let me go ahead and click on here somewhere and hit equals. Okay, so it gives me an answer. If I go back up here and get an answer that doesn't let me use figure 1, okay, so I can't use this little program because it says the AASHTO figures are not appropriate here. And you could change that to say something else, but um, I'm just showing that my program seems to be working okay. So let me go back up, make this 0, and scroll down. All right, so I've got it set up so if I use figure 1, then there's some other things I've got to check. The first thing I've got to check is, well, is theta outside of my boundary? If theta is greater than 120, then it's going to send me an error message. So let's go up and type in 122 or 121. Yeah. So first thing it does is checks the value of theta and says, okay, hey, it's outside the bounds. It gives me an error message, and that's basically telling me that in case something happened up above, where it would say use the wedge method, this is another check to make sure that I don't just willy-nilly do something that I shouldn't. So I try to handle errors in all the programs that we write in MathCAD. So let's go back up, make this 120, and now it should recalculate some value. All right, so theta is not greater than 120, so it will go to the next program statement. So if theta is equal to 120, then it's going to look up the value of the theta equals 120 chart. So let me pull this over here just a little bit, just so I can show you. So here's the 120 column right here. Here's my 30 degrees. And so the value that it should return is 12.99. And it does. Now, how did it do that? Well, what it does is that when you type in the lookout, the first argument that you give it is the variable that you are wanting to look up. So in this particular case, the chart value for phi, which is 30, is the value that it looks at. And then the second one looks at the table value of phi. Let's see, where did I do that? Let's see, I kind of forgot what I did there. Phi table. Oh, okay. Yeah. All right. So phi table is the vector that I created up here in the. There we go. Phi table is the vector of internal friction angles from 0 to 45 in half a degree increments. Okay. So I give it the value that I want it to look up. In this case, it's 30 degrees. Then I tell it which vector that I want it to look up. And then I have to tell it, well, which vector do I want to find the corresponding value for the angle of internal friction? And so what the lookup table does, and it's the same in Excel as it is in MathCAD, is that once it goes to a position, say 30 degrees, it moves over to the vector that you want to search in and goes to the same position. So in this case, it's position 62, and it pulls the number out of position 62 and returns it back to MathCAD. So it's that 12.99 that it looks at. All right, so remember that is a index. So VY1 indexed 1 is my 120 table. And so it goes in and finds the 60-second value and pulls it out of that. All right, so let's say it's not 120. Let's say it's 110. I should get a different value, and I do. I get 10.13. So that takes me over to the second index, and there's my 10.13 and my underneath my 110. So you see how that works. So once it finds the position, then it goes into all these different vectors and looks for the value at position number 62. So another thing that I did is that I went in and in the chart or the Excel spreadsheet that I sent out earlier, I had all these as blank because the curves, they kind of stop at 5, but I think that's more of a function of the pictures trying to be legible. I think they all curve to 1, so I went back in and put those numbers in. And then the other thing I did is that everywhere there is no number, so example on curve 120, it hits the peak value at about 31.5, something like that. Everything after that's not really a number. So NaN is computer jargon for not a number. So if you see a not a number where you're expecting a number, then you have to investigate and see what's going on. All right, so let me move this over. So you can see I've done this all the way down until I get all the way out of the 50. So that's the lowest curve that I have. And then I make another check and I say, okay, if theta is less than 50, then something's gone wrong. So it should send me an error. So if I type in 49 here, then I should get an error message, which I do, which is great. All right, let me go back to 50, and now it gives me an actual value. Okay, so the next thing I need to do, well, what if I need to interpolate between some of these curves? Let's say I need to interpolate between 50 and 60 or 60 and 70. How do I do that? Well, the way I did it is that I want the program to output some additional data. So if, for example, theta was between 110 and 120, then what I needed to do is say, okay, I need it to go in at 110, look up the value, spit it out in the program, and then I'm going to go ahead and tell the software that it's 120 degrees, so I know where it works out, so I don't have to pay that much attention to it. I want it to do it automatically to tell me which chart it went to. Although to be honest with you, it would be pretty easy. All you got to do is look at this theta number, and it tells you where you are. But let's just do it this way. So it gives me the theta value or the passive pressure value at theta is 120, and then it spits it out at 110. And then I'm going to use an interpolation function to interpolate between those two values. All right. So let me go up here and type in. Let's change this to. I can't make it greater than 120 because then I get an error message. Let's make it 112. So 112 is between 110 and 120. So it's given me 4 pieces of information. In the first column, it gives me the Kp value at theta equals 120. In the second row of the first column, it gives me the Kp value at 110. In the first row of the second column, it gives me my theta value, unfortunately that's in radians. And in the second row, second column, it gives me my theta value of 110 in radians. All right, so now that I've got that information, I've got to figure out what do I do with it. So what I do is that I regurgitate the matrix that I find in this program that I wrote. Okay, so here it is. So these are the four values we just looked at. If I go in and change this value, let's say I make it 91, then you can see that I've got this matrix, which will be the same right here. So I'm just retyping it, and the only reason I'm doing this is just to make it easy to program it and to explain it. Once we get this thing worked out, we can delete it because we don't need it anymore. But if it returns a single value, then I know that I don't need to interpolate anything. But if I get more than more than one value, then I know that I've got to move on to an interpolation. All right, so how do I do that? Well, I've got to come across a check. So what I'm going to do is I'm going to type in this little variable that says the length of this vector is 2. So I take the name of the vector and then I use my column. It is this little dude right here, the second from the top on the vector operations. So here's my column. So if you give it the length, you can't give it the length of a matrix. You have to give it the length of a vector. Okay, so I use the column sign, and so it's telling me that the length or the number of rows in my columns is 2. So that anything greater than 1 means that I've got to do some interpolation. So how do we interpolate? Well, I went to some textbook. I don't know where I found it, but so I found this little formula, and basically the formula is that the interpolated value, in this case I'm assuming it's y, is equal to one of the points, y1, plus, and then we've got this ratio here. So, and then I actually did it the hard way, got the right answer, and then I found the formula. And when I say hard way, I just do it like I always do it. You write down the numbers, and then you figure out how to do it. So I wrote a program that does exactly what I'm talking about here. Let me close this. So the answer is 6.641. I've got 6.641. That's too many decimal points. Let's change that. Make it 2. I'm sorry. 2. Let me do the same thing here. All right. And let me close this because you can see that I get the right answer. So here is let's call it a, maybe a more, it's not simple, but it doesn't take advantage of the power of MathCAD. So I just did this by brute force, okay? So it says if the length is greater than 1, then I calculate my x value, which is just theta, my y1, x1, delta x, delta y, and then I use that same formula that I had up here, and I just cut and paste it so that it fits perfectly there, and then it just spits that number out. But there's another way to do this, so I wrote another program. I think I did. Where'd it go? It was here just a minute ago. Well, that's a mess. Hope I didn't delete it. Well, it's gone somewhere. Let's see if I haven't moved over anywhere. Doesn't look like it. Well, I have it in the MathCAD has a little interpolation function. and it just takes three variables. So you give it an x value, you give it a y value, and then you give it the value that you want to look up. Let's see if I can recreate it here. Um, so len, and I'm going to give it a let me copy this here so I can see it. Okay, so here's my x values, here's my y values. Is that right, or did I do them backwards? Oh, that's right. I've got to. So one of the tricks in when you use the linear interpolation function is that your matrix has to be in ascending order. Well, unfortunately, this one's not. It's in descending order. So there's a little function called csort. Uh, let's see. Let me show you where the functions are first. Functions, all functions. Now I got to figure. Well, there's my lookup functions. I tell you what, instead of putzing around like this, because it took me a while to figure this out, let me recreate this, and I'll either add on to this video or I'll shoot a quick next one. But so just to recap, what we've done is that we have checked to see if we can use figure one, and if we can use figure one, then we have come up with a little program that actually will look up the values of theta from 120 to 50 and will interpolate between intermediate spaces if necessary. Also, the program will tell us if we can use the AASHTO method or not, and then again, we have not figured out what to do with figure two. That'll be next. And so I'll put that out here in a little bit as once we get that done. And then I may update on this little program that I did using the linear interpolation function. Okay, turns out that I only thought I programmed it in my head. I didn't actually do it anywhere in the spreadsheet or the MathCAD template. I just thought I'd done it. So I went ahead and did it. So here's so again, here's the new program that I wrote. You can see it's got only really 2 lines of code as opposed to the 1, 2, 3, 4, 5, 6 lines that I did when I didn't take advantage of some of MathCAD's internal functions. So I get the same answer, so I can close this. And let's show you what I did. In order to use the linear interpolation function, you've got to have a vector that's in ascending order. So to do that, here's the various sorting arrays that we have. If you have a vector, you can sort it in ascending order. If you can do a reverse sort that sorts it in basically R sort rearranges the column in ascending order. Try again. Sorts a vector into ascending order. Reverses that, so it'd be in descending order. And then C-sort and R-sort are the same thing for a matrix. So the arguments for C-sort are you need to tell it, well, which matrix do you want to sort, and also which column that you want to sort. So if you have a 2x2 matrix, you can give it the name of the matrix in either column 1 or column 2. So let's move this over here. So again, I've got the same initial if statement. If the length is greater than 1, then I've got to do some interpolation. So I and the, I don't really need these. Okay, but I just put them in there to help explain. So here's the original matrix that came from the program. Here's how I sorted it. You can see that it sorts the 6.473 stays with the 1.571 like you would expect, but it goes in ascending order, and I sorted it on column 1. In this case, it didn't matter because it didn't matter, but sometimes it does matter. So the program is, all right, I call the sorted matrix M, and then I call this linear interpolation function. So I just remembered that if you if you know what the function is, but you want to use it from here, the nice thing about this is that it tells you when it pulls it up how many arguments it expects. Here, it expects 2 arguments. That's on this particular thing. You don't have to plug the formula in. You can actually type it. But it's nice to know what the arguments it expects without having to look it up. So it's really simple. You linear interpolate. You put in the x values, you put in the y values, and then you put in the value that you want to interpolate from, and it does it for you. So in this case, if length is greater than 1, interpolate. If not, just return the original number from the program. So let's go in there and check and see if this works. Let me go back up and change it so that my function here only outputs 1 value, and it should do that anytime you type in something like 50, 60, 70, 80, 90, any increment of 10. There we go. All right. So it gives us a 5. None of that works because that was a demonstration. And here we go. We get the number 5. All right. So that works. And so we have completed how we would go about creating a MathCAD template to determine the passive pressures, or the passive pressure coefficient, rather, according to the AASHTO method. There's 2 figures, figure 1, figure 2. We've just worked on figure 1. In the next video, I'll do something very similar and have a function that, if you can't use figure 1, will automatically take you to figure 2, or whichever you get from chart check.